Welcome to IG Career Institute. So I think you have already viewed where I have solved the first 10 questions of FG 2022 chemistry paper, and this is the part 2 video where I will be solving the next 10 questions. So let's start. So we will be starting with the 11th question, and this question says the correct bond order of BF bond in BF3 molecule is. Now in order to find out the bond order of a particular molecule, let me first draw the resonating structure. So first of all, what's the structure of BF3? It's a trigonal planar geometry where the lone pairs of the fluorine are resonating. Therefore, boron will have a negative charge and fluorine will have a positive charge. Now, this fluorine will may also donate its lone pair and undergo delocalization. So, overall, we will get 3 resonating structures. So these are the 3 resonating structures of BF3. Now, in order to find out the bond order, there is a formula. Now, what's the formula? Bond order equals to number of resonating bonds between any one BF bond divided by total number of resonating structures. Now, what does this formula tells us? Number of resonating bonds between any one BF bond. So, you have to consider any single BF bond, either this or this BF or this BF. Now, compare it with the rest of the structures. Now, if I consider this BF bond, the first BF bond, then how many bonds are between these 2 elements B and F? 2. In the next structure, between the same boron and same fluorine, how many bonds are there? 1. And between the in the next structure, between the same elements, how many bonds are there? 1. So total, how many resonating bonds are between these boron and fluorine? Total 4. So in the numerator part, we will be writing 4. And how many resonating structures in total are there? There are 3 resonating structures. So that divided by 3. So that comes as 1 whole 1 by 3, and which is our option D. So correct option is option D. Okay, so the next question given to us is the correct order of acidity of the following hydroacids is. So we have to predict the proper order of acidity of HF, HCl, HBr and HI. So let's start with HF. Now, hydrogen fluoride, it has a strong bond. It has rather the strongest bond among these all 4. Why? Because the bond dissociation energy of this HF bond is quite high. Owing to the high electronegativity of fluorine atom and its small size, thereby the bond between hydrogen and fluoride is quite strong. Now, as the hydrogen and fluoride bond is quite strong, HF won't have or will be quite reluctant to leave its hydrogen. Hence, the cleavage of this bond will be quite difficult. And thereby HF will exhibit lower acidity. Okay, so we already know that whichever compound releases its proton easily into the medium, that has high acidity. Now, if this bond is strong, this cleavage is not possible. That means HF has lower acidity. So, following the trend in the periodic table, we know fluorine has greater electronegativity, then comes chlorine, then comes bromine, and then our iodine. So, the HI bond is the weakest amongst all these 4. So, the bond dissociation energy is less in case of HI. Now, as the bond dissociation energy is less, the cleavage between HI will be higher, hence cleavage will be easier, hence acidity will be higher. and in this case bond dissociation energy higher, so cleavage will be difficult, and hence acidity lower. And so the following this trend, finally, which will be the proper order? Hydrogen iodide will exhibit higher acidity, next HBr, next HCl, and finally HI. So which matches this option? That is this one. Hydrogen iodide has maximum acidity, then hydrogen bromide, then HCl, then HF. So this is in increasing order. So basically this will be the correct option, option B. Okay. So this is question 13. To a solution of colorless sodium salt, a solution of lead nitrate was added to have a white precipitate which dissolves in warm water and reprecipitates on cooling. So which of the following acid radical is present in the salt? We are given with 4 options. Now from this question, from which part we will take the clue? That is the white precipitate. It's talking about the white precipitate which dissolves in warm water and reprecipitates on cooling. We already know such the white precipitates which actually dissolve in warm water and can be reprecipitated on cooling is actually lead chloride. So basically the solution of colorless sodium salt, basically that was sodium chloride. So how the mode of the reaction is going on? Lead chloride was first treated with a solution of lead nitrate, that is PbNO3 whole twice, arrow, it's just a double decomposition reaction, PbCl2, this is the white precipitate, plus 2NaNO3. So this is basically the white precipitate which dissolves in warm water and reprecipitates on cooling. So chloride radical is basically present in the medium. So our correct option is option A. So let's move on to the question 14. Oxidation states of chromium in K2Cr2O7 and CrO5 are respectively. So we have to predict the oxidation state of chromium in these two compounds, in these two given compounds. So K2Cr2O7. So how can we find the oxidation state of chromium? Let it be X. So how many chromium are there? 2. So 2X plus, for potassium 2 minus, for oxygen it's a radical, negative radical. So for that minus 2 plus minus 2 into how many oxygen atoms are there? 7. So that equals to 0. Now if I calculate it, 2x plus 2 minus 2, 7, 14, that equals to 0. So that will come out as 14 minus 2, that is minus 12. If I move it on to the right hand side, it will become plus 12. So x will come out as 6, plus 6. Right. Next, let's move on to CrO5. CrO5. Here we have to find out the oxidation state of this chromium. Let it be X or Y, because once we have already considered X. So let it be Y, and in this structure for chromium, here oxygen, all the oxygen won't be exhibiting minus 2 charge, because the structure predicts like this. There are four peroxide linkages. So for that peroxide linkages of these 4 oxygen, we have to consider minus 1. So, and 1 oxygen is in divalent character only. So like for this oxygen which is doubly bonded to chromium, for it the negative charge will be minus 2. So Y minus 2 for this oxygen, and for the other 4 peroxide linkages plus minus 1 into 4. That will that's basically equals to 0. Right. Because the molecule overall is neutral, so Y will come out as minus 2. If I move it on to the right hand side, plus 2, and this minus 4, if I move it on, then it will become plus 4. So basically plus 6. So in both the compound, the oxidation state of chromium is coming out as plus 6. So basically, which is the correct option? Option C. So question 15 is, the correct order of relative stability for the given free radicals is. So we have to compare the stability between these 3 given compounds, rather these 3 given radicals, 1, 2 and 3. So how can we compare these 3 radicals? Which will have the greatest stability? See, radical means 1 unpaired electron will be present on the carbon atoms. So if these electrons the charge density, that carbon will be stable if this charge density is neutralized or lessened by some other functional group. See, in this compound 3, there are two electron withdrawing groups, COOET and NCH3 whole twice. Owing to the electronegativity of these two groups, they will be pulling the charge density from the carbon center, thereby neutralizing this or stabilizing this species more. As compared to with 2, there are only one electron withdrawing group present. No COET is there. So the stabilization will be less as compared to 3, and in 1, see, there are no electron withdrawing group. Only CH3 is present, which is actually electron donating group. So basically overall, the 1 will be the least stable among these 3. So 3 will be more stable, then Roman 2, then Roman 1. So which is the correct option? Option D. Question 16. Here two carbon ions are given, 1 and 2, and you have to state the hybridization of the carbon bearing the negative charge. Okay, so generally carbon ions are sp3 hybridized. The carbon carrying the negative charge in a carbon ion are generally sp3 hybridized. So 1 is obviously the carbon where the negative charge is present, it is sp3. But generally, if there is a possibility of resonance in a compound, then the carbon bearing the negative charge is generally sp2 hybridized. Why? Let me tell you. See, CH2 minus, what's the compound here? CH, yes, C double bond O, H, CH3. This is the compound given. So if this negative charge is involved in resonance, then this negative charge must reside in the vacant p orbital, otherwise this resonance is not possible. So under such situation, this carbon must be sp2 hybridized. So basically 1 is sp3 and 2 is sp2. So this is option B. Option B is our correct option. So the next question is, we are given two compounds, two structures whose we have to predict the correct relationship between them. So the two structures, this is given in a bit twisted in a inverted way. If I rotate this molecule, we will find that these two molecules will be superimposable upon each other. Now the condition for being homomer, we know that two structures have to be superimposable on each other. So if I rotate this molecule, we will find out that this molecule is being superimposable on this compound, hence B will be our correct option. So the question 18 is, the enol form in which ethyl 3-oxobutanoate exists is. So first of all, we have to draw the structure of ethyl 3-oxobutanoate. So ethyl, that is C2H5 oxobutanoate. There have to be 4 carbon atoms, 1, 2, oxo at 3 position and CH3. So 1, 2, 3, 4. See, at 3 position I have put the oxo functionality, that is the ketone functionality, and then there's butanoate functionality at carbon 1, and ethyl is attached with the oxygen here. So this is basically the structure of ethyl 3-oxobutanoate. Now this middle hydrogen is quite acidic, and rather this will undergo tautomerization. Now there are two carbonyl functionality both on left and right hand side, but on the right hand side these carbonyl functionality is already in conjugation with the lone pair of this oxygen atom, so it will have less probability to undergo tautomerization. So this hydrogen basically will undergo tautomerization with this left hand side carbonyl part. So after undergoing tautomerization, how will the structure look like? CH3CO, the hydrogen will come up here and the double bond will form here, CH, and the rest will remain as it is. Now in this conformation, there will be a possibility of forming intramolecular hydrogen bonding. So basically, if I bend this molecule a bit, like if I draw it in the proper zigzag place, then there will be a possibility of intramolecular hydrogen bonding, which will provide additional stability to this compound. So basically, which is similar to this structure? That is our option C. Here basically the CO2, C2H5 are drawn in a condensed form. If I draw it in the entire structural form, then we will get back to this. So option C is the correct option. Question 19 is, how many monobrominated products including the stereoisomers would form in the free radical bromination of N-butane? So let me draw the structure of N-butane. It's very easy. Just 4 carbon atoms, just normal butane. So just see, if I replace like if the bromination takes place in this carbon atom or in this carbon atom, and we have to consider only monobromination, we don't have to consider the subsequent reactions. So if I consider monobromination, that is if one hydrogen here is substituted with a bromine, similarly here also if one hydrogen is substituted with a bromine, in both the cases, we will get similar product. So if this hydrogen is substituted by bromine or this hydrogen is substituted by the bromine, we will get similar product. So for that one monobromination, we will basically get on either of these carbon atom, we will get one structure. Now if I consider the second molecule, CH3, CH2, CH2, CH3. Now the second carbon atom and the third carbon atom are equivalent, right? So if I consider here one of the hydrogen will be replaced and bromine will be substituted, then this carbon will become chiral, because this carbon is now attached to 4 different groups. In one hand it has methyl, in the other it has ethyl, in another hand it has hydrogen, and in the last hand it has bromine. So it is a chiral center. Now for chiral center, we know there is a possibility of plus isomer, that is D isomer and A isomer. So we will get a plus minus isomer, therefore total 2 stereoisomers of this particular compound is possible. Hence in total overall we will get 3 monobrominated products. So the correct option is C. So the next question, question 20 is, what is the correct order of acidity of salicylic acid, 4-hydroxybenzoic acid and 2,6 dihydroxybenzoic acid? So let me first draw the structure. What is the structure of salicylic acid? That is, it is basically, there is a OH group with respect to COH group in the ortho position. So this is the structure of salicylic acid. Next, what do we have is 4-hydroxybenzoic acid. This is the hydroxy group, rather here's the COH is in para position. This is the 4-hydroxybenzoic acid, and the last one is 2,6 dihydroxybenzoic acid. So the dihydroxy are in the 2 and the 6 position, that is both the ortho positions are filled with 2 OH groups. So basically what happens here, this OH and this COH, so basically whichever compound will release its proton easily, that will have greater acidity. So here in this compound there are 2 OH group in the ortho position with respect to COH group. Now there won't be any hydrogen bonding because the COH group and the OH group are not in the planar position because of the bulky size of the COH group. These 3 won't be in the planar position, so no possibility of hydrogen bonding. So this proton will be released faster and the conjugate base will look like this. So this conjugate base will be more stabilized due to the presence of 2 OH group and due to the extended conjugation through the phenyl ring. Here also the proton will be released and this base, conjugate base, will also be stabilized via extended conjugation through the OH group. But here the additional effect is, there is the inductive effect of OH group is also operating, but here the OH group is in the para position, hence the inductive effect doesn't operate after 3 carbon atoms. So here there won't be any inductive effect, only extended conjugation parameter. And here also if this proton is released, then the conjugate base of this compound will look like this, and here the minus charge will be stabilized via extended conjugation through the phenyl ring as well as via the inductive effect of this OH group. So here due to the presence of 2 OH group, the stabilization of the entire compound will be more. Then due to the presence of 1 OH group, here both inductive effect and resonance are operating. So the stabilization will be after this compound, and this will be the least stable because there is no inductive stabilization, only resonance stabilization. So the order will be First will be 2,6 dihydroxybenzoic acid, next will be salicylic acid, and the last will be 4 hydroxybenzoic acid. So the correct option is option A.